Okay, let's go over 8.4. De Moivre's theorems, powers and roots of complex numbers. So De Moivre's theorem says if R CIS theta is a complex number, n is an element number, then R to n, CIS theta n is equal to R to the nth CIS n. Basically what we covered in the previous section, the power rule, but it's kind of like the product rule that we talked about previously here, where we're doing R1, R2, but in this case, all the R's are the same and all the thetas are the same. So we just multiply the number of thetas together, like n thetas, and R just gets raised to a power, okay? Because multiplication, exponentials is fast multiplication and multiplication is fast addition. If the complex number a plus bi is an nth root of the complex number x plus yi is an nth root, okay, of the complex number x plus iy if a plus bi to the nth is equal to x plus yi. Find radical 2 plus I, radical 2 to the 5th power, and write the answer in rectangular form. Okay, so what I'm going to do is I'm going to translate this to trigonometric form, use de Moivre's theorem here. Okay, so we know that x is equal to radical 2, y is equal to radical 2, okay, because it's in a plus bi form. I mean, we'll call it a and b. Okay, and so what's r going to be? Because we want to get r and r and theta. Okay, so r is going to be the square root of radical 2 squared plus, or a squared plus b squared. Now I'll write that out. So it's going to be a squared plus b squared, right? So that's going to be equal to the square root of 2 squared plus the square root of 2 squared, because a and b are radical 2. Well, radical 2 squared is just 2. And so the radical and the squareds are going to cancel, the radical underneath the big radical. And so this is 2 plus 2, which is 4, which is 2. So we know r is 2. Okay, so that's helpful. R is 2. What about theta? What's theta going to be equal to? Well, theta is the inverse tangent of y over x, or b over a. Okay, and in this case, this is the inverse tangent of radical 2 over radical 2. Okay, so the inverse tangent of radical 2 over radical 2, which is the inverse tangent of 1. And this is going to be equal to 45 degrees in the first quadrant. Are we in the first quadrant? Yes, we are, because both the x and the y, or the a and the b, are positive values. So we are in the first quadrant. So our theta is 45 degrees. Okay, so we know that this is going to be r of, so we RCIS theta to the 5th power, okay, is going to be equal to 2 CIS 45 to the 5th power, which is going to be 2 to the 5th power, according to De Moivre's theorem here. Okay, that's going to be 2 to the 5th power, CIS times 5 times 45. Okay, so if I do 5 times 45 on the calculator, I believe that's 225. We'll just verify it. Okay, so 5 times 45 is 225. Okay, so this is going to be equal to 2 to the 5th CIS 225. degrees. Okay, and 2 to the 5th is 32. Okay, so this is 32 CIS 225. Okay, and then what is that going to be in terms of, going back to rectangular form? They want the answer in rectangular form. So this is in trigonometric form. Okay, I want to go back to rectangular form. Okay, so 32 CIS in rectangular form. Okay, so x is going to be equal to 32 times the cos of 225, and y is going to be equal to 32 times the sine of 225. Okay, the cosine of 225 is radical 2 over 2. Sorry, negative, because this is in the quadrant 3, right? So 225 is in quadrant 3. So on the unit circle, I'll make that a little higher. On the unit circle, it's right here. And so what's cosine and sine? Well, it's negative radical 2 over 2, negative radical 2 over 2, okay, on the unit circle there. So this is going to be 32 times negative radical 2 over 2. 2's are going to cancel, leaving me with negative 16 radical 2. Okay. So let me do it like this. It's getting a little crowded here. X is equal to 32 times negative radical 2 over 2, which is equal to negative 16 radical 2. And the same thing is going to go for y. Y is equal to 32 times negative radical 2 over 2, which is equal to negative 16 radical 2. Cancel those. Okay. And so what is this going to be in terms of rectangular form? It's going to be negative 16 radical 2 plus, or minus, I should say, minus 16 radical 2i. Okay. Okay. The nth root, okay, the nth root, think of a non-complex number r CIS theta has n distinct nth roots given by the cube root of r CIS alpha, where alpha equals theta divided by n this time. Okay, so theta divided by plus 360 times k over n, where k equals 0 to n minus 1. Okay, so there's a bunch of values there. Okay, there are n values, it's just we start with 0 instead of 1. Okay, so we're going to get n roots. Okay, n roots. Okay, now what's happening here with this theta divided by n? Okay, think of it like this. If we had r CIS theta, but we raised it to the 1 over n, wouldn't that be r to the 1 over n, or the nth root of r? Okay, and then instead of, and then multiplying by 1 over n, well, that's the same thing as dividing by n. So this would be CIS, put this over here, actually. So we have r CIS theta to the 1 over n is equal to r to the 1 over n CIS theta times 1 over n. Okay, 1 over n. Okay. So this is going to be the nth root of r times CIS theta over n. But there's, if we start with theta and we divide it by n, there's more than one value that will work for that. Okay, and that's why we call this thing alpha. Okay, this thing here is going to be alpha, where alpha, so this is going to be the nth root of r CIS alpha, where alpha is equal to that theta over n, but it's going to have n n angles. Okay, we're dividing theta by n, but every n partition in that angle is going to have a value. Okay, and so this is plus k 360, or 360 times k, all over n. Okay, so instead of cycling every 360 degrees, it's going to cycle every 360 over n degrees. Okay, and where k equals 0, 1, dot, 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 upward, up to n minus 1. Okay. Okay, so let's take a look at this. Okay, so the rest of the definition is, you know, for n is a positive integer, r is a positive real number, and theta is in degrees. Yes, that's good. Note that if theta is in radians, we replace 360 with 2 pi. Okay, find 3 cube roots of radical 8. Okay, 3 of them. Now you might think, well, there's only one cube root of radical 8, and that's -2, and that is correct, but those are real numbers. And remember, we're working with real and imaginary values here. So if I take the cube root of -8, I do get -2, but that's only one real root. Okay, I want imaginary roots as well. So here's how we do this. We're gonna take, okay, -8, and I'm gonna say, okay, well, what is -8? How can I write that in trigonometric form? Okay, so -8, if we look where we are on the unit circle, okay, or on a circle, if I go out this direction 8, I'm at -8 on the number line. Okay, and so how would I think of that in terms of radius and angle? Well, the radius would be 8, and the angle would be what? Yeah, the angle would be pi. So this would be 8 CIS pi. Okay, and that's going to give me a value of -8, okay? If I were to plug that in, okay, for x is equal to -8 cosine pi, or 8 cosine pi. Okay, and cosine pi is -1, so that just becomes -1 times 8, which is -8. That's correct. Y is equal to 8 sine pi, and the sine of pi is 0, so 8 times 0 is 0. It goes to 0, which is 0. So that does come out to be the correct point. Okay, so 8 CIS is the trigonometric form of -8. 8 CIS pi, I should say. Okay, so now I'm going to take the cube root of this. Okay, so how do I do that? Well, it's the cube root of 8 times CIS pi over 3 plus, okay, 2 pi k over 3, okay, for k equaling, okay, k equaling 0, 1, and 2. Right? Okay, well, the cube root of 8, well, that's just 2. Okay, that becomes a 2. Then I have CIS pi over 3, and then I have 2 CIS, if I plug in a 1 here, that's pi over 3 plus 2 pi over 3, which is 3 pi over 3. So I'll plug in if I plug in the 0, well, maybe I'll do it so that it's, if I plug in the 0, this whole thing goes to 0, right? So we're just left with 2 CIS pi over 3. I won't skip steps. Okay, this thing is going to be 2 CIS pi over 3 plus 2 pi times 1 over 3. Okay, so this is going to be 2 pi times 1 is just 2 pi. They're over that common denominator of 3, so 2 pi plus pi is 3 pi. So this is 2 CIS 3 pi over 3. And that's going to reduce to just pi. Okay, so this is 2 CIS pi over 3. And then we get 2 CIS pi. Okay. Okay, and then we'll get the last one here. Okay, this is going to be 2 CIS 2 pi over 3 plus 2 pi plus 2 pi times 2 over 3. Okay, so what is this going to be? This is going to be 2. Okay, or it's not, sorry, it's just pi over 3, not 2 pi over 3. I think. Okay, so what's that going to be? That's going to be 2 CIS. This is going to be pi over 3 plus 4 pi, which is 5 pi, right? So that's 5 pi over 3. Okay, so 2 CIS 5 pi over 3. Okay, so now what I need to do is change each of these into their rectangular components here. Okay, so 2 CIS pi over 3. Okay, what is that going to be? Well, x is equal to 2 cosine pi over 3, and y is equal to 2 sine pi over 3. Okay, cosine pi over 3 is, let me think about that for a second. Cosine pi over 3, that's the x value, so that's 1/2. Okay, the sine pi over 3 is radical 3 over 2. Okay. Okay, so this is going to be equal to 2 times 1/2, which is 1. Okay, and then y is going to be equal to, let me zoom in a little bit. Okay, y is going to be equal to 2 times radical 3 over 2, which is just radical 3. So the rectangular form of this is 1 plus radical 3i. Okay, so that's my first one. Okay, what about the next one here? The next one I have 2 CIS pi. Okay, so 2, so x here is 2 times the cosine of pi. Well, the cosine of pi is -1. And so that's just -2. Okay. And then y equals 2 times the sine of pi. And the sine of pi is 0. And so this is 0. Okay, so this is going to be -2 plus 0i, which is just -2. That's the real value that we got before. Okay, so we get -2 plus 0i, but 0 times I, that just goes away. And so we're just left with -2. I don't know. Okay. Okay, the next one here, the last one. Okay, 2 times CIS. Okay, 2 times CIS 5 pi over 3. So where is 5 pi over 3 located? Well, that's going to be just slightly smaller than 6 pi over 3, which is 2 pi. And so this is going to be in the 4th quadrant. Reference angle is pi over 3. Okay. And so still the x value is going to be 1/2, but the y value is going to be negative radical 3 over 2. Okay, so very similar to what we had before. So x is equal to 2 times cosine 5 pi over 3. Okay, and y equals 2 sine 5 pi over 3. Okay. I'm going to move this over a little bit. So I can get in there. Right. Okay, and then this is going to be equal to, okay, the cosine of pi, that was still 1/2. So this is going to be 2 times 1/2, which is 1. Okay, so the next one is going to be, this is going to be now negative radical 3 over 2. So this is 2 times negative radical 3 over 2. 2's cancel out, and I get negative radical 3. So this is really going to become 1 minus radical 3i. Okay, and so I have my 3 roots, my 3 complex roots for that problem. Okay, so a lot of work on that one. Okay, let's look at the next example here. It says find all 4th roots of this guy. Okay, so all 4th roots. Okay, so this is in rectangular form. Okay, I'd like to get it into trigonometric form. So what I'm going to do, first I'm going to factor out that 128. So this is 128. Okay. Times, I'm going to get this negative 1 minus radical 3. Okay. Radical 3i. Okay, now that looks very familiar. Now if I were to, if I could get this to be a 1/2, then I got an angle for theta that I can get directly here. Okay, cosines and sines. So if I pull this out, if I pull out, if I multiply both top and bottom by 2, okay, I pulled out the 128, but if I multiply both top and bottom by 2 here, 2 over 2, okay, then I can distribute the 2 to the 128, that becomes 256. And I could distribute the negative 2, or sorry, not the negative 2, the 1/2, the 2 on the bottom here, I could distribute that 1/2, this is like 256 times 1/2, times negative 1 minus radical 3i, and I'm going to distribute that 1/2 inside, okay? So this is negative 1/2 minus radical 3 over 2i. Okay, and what angle is this going to be? Where is negative 1/2 x? Where is x equal to negative 1/2, but y equal to negative radical 3 over 2? Okay, well, we were just dealing with x's and y's that basically have these values. Okay, and this is going to be live in the 3rd quadrant, and this is going to be 4 pi over 3. Okay, so at 4 pi over 3, okay, we get this guy here. That's the angle. Okay, that's the angle there. Okay, so now what would r be in this case? What would the radius be? We found theta to be equal to 4 pi over 3, but what would the radius be? Well, if I found r, okay, r given just just this value here, wouldn't R be 1 because it's on the unit circle? Yeah. And we're just going to say, well, this thing that's on the unit circle that has a radius of 1, okay, so this portion of it here that's highlighted has a radius of 1, but then it's just being multiplied by 256. So the radius is 256. Okay, that's the radius. So we would really get 256 CIS times 4 pi over 3. Okay, but we want all 4th roots of this. So we're really raising this to the 1/4 power. Okay, we want the 4th roots. Well, what's the 4th root of 256? Okay, so this is going to be the 4th root of 256 times CIS 4 pi over 3 plus 2 pi k over 3. Okay, and we have 4 roots, so k is going to be 0, 1, 2, and 3. Okay. So let's start with the 4th root of 256. The 4th root of 256, if I take 256 and I raise it to the 1/4 power, I get 4. Okay, so this is going to be 4 CIS, and then it's going to be 4 pi over 3 plus 2 pi k over 3. Now, they didn't ask me to put it in rectangular form, so I'm just going to leave it in trigonometric form, which will save me some work. But I do need to get each value here for k equals 0, 1, 2, and 3. Now, it's just working with fractions, basically. Okay, I'm just adding 2 pi on the numerator each time. So that if I let k be 0, I just get 4 pi over 3. So this is 4 CIS 4 pi over 3. That's my first one. If I let k be 1, I have to add a 2 pi, and that gets me 6 pi over 3, which is just 2 pi. So I get 4 times CIS 2 pi. Right, because 4 plus 6, yep, it's 2 pi, so 2 pi. Okay, and that just ends up being 4. Okay, and why? Because we're located at 2 pi, which is really the same thing as 0, which means the angle is 0, which means we're on the number line, which means we're out 4. Okay, this really is an angle of 0 because it's 2 pi. 2 pi is the same as 0, and so the cosine will give me a 1, and that'll create 4, and the sine will give me a 0. So I'm really just out on the number line 4. So this really is just 4. Okay, but we can leave it. We can leave it as CIS 2 pi. We'll leave it in trigonometric form. It doesn't matter. I don't need to go to rectangular form for this one. Okay, then we're going to go for CIS. Okay, now what happens if I multiply this is 4 plus 4, which is 8. So that's going to be 8 pi over 3. Okay, and again, these values are above 2 pi, or above, no, they're not above 2 pi. They shouldn't be. 8 pi over 3. Let's see. Yeah, I guess they are. That's fine. That's fine. Okay, but we could reconcile that if we wanted to. I'm not going to. I'm not going to make it within 1. So that would just be 2. It would really end up being 2 pi over 3, but it's fine. It's fine. And then if we plug in 3, we get 6 plus 4, which is 10. So that's going to be 10. So for CIS 10 pi over 3. Okay, and we can leave it like that. That's fine. We don't need to mess with it anymore. Okay, last example. Find all complex solutions of x to the 6th I equals 0 graph them as vectors in the complex plane. Okay. So how am I going to solve this? Well, we get x to the 6th plus I equals 0. Okay, so this becomes, if I toss the I to the other side, subtract I, okay, I get x to the 6th equals negative I. And then I'm going to say, well, this is going to be the 6th root. Okay, of both sides, and we get x is equal to negative I to the 1/6 power. Okay. However, this is an imaginary number or a complex number, and I'm going to write this as 0 minus I, just so that I have an x component and a y component. Okay. Okay, and so x is 0 and y is negative 1, right? X is 0, y is negative 1. So where would this be graphically? It would be down here. Okay. Where on the real axis, I'm at 0, and the imaginary axis, I'm at negative 1. Okay, so maybe I'll put a dot in black where that's located. It's located right there. Okay. And so if I were to change this to trigonometric form, what would it be? Oops. Well, what would what's the radius? The radius is just 1. Go back. Okay. The radius, the length, okay, is 1. The radius is 1. Okay, so r is equal to 1 here. Okay. And then, because what I want to do is I want to turn this into trigonometric form, 0 minus I. What is that in trigonometric form? Then I can take the 1/6 of that and use de Moivre's theorem. Okay, so r is equal to 1. Okay, that's nice. And then what's the angle? What's theta? Well, theta is just 270 degrees. Okay, or 3 pi over 2. Maybe I'll do it in degrees to make it a little easier. So let's do this in degrees, I guess. Okay, 270 degrees. Okay, so now what do we want to do here? Well, this is going to be r CIS theta to the 1/6 power is the same as the 6th root of r CIS theta over 6, right? Plus, it's instead of 2 pi, it's going to be 360k over 6. Okay, where k is now equal to 0, 1, 2, 3, 4, and 5. So a lot. Okay. Okay, so let's see what we get here. Okay, so well, what's r? R is 1. What's the 6th root of 1? Is 1. So okay, so this is going to be 1. Okay, CIS theta over 6. And what's theta? Theta is 270. 270 degrees over 6. Okay, does that divide evenly? 270 divided by 6, 45. Yeah, that's great. That's awesome. Okay, so that's 45. Okay, so this is 1 CIS 45 degrees plus, okay, I should put this in parentheses, okay, plus 360k over 6. Okay, and what's 360 divided by 6? Well, that's just 60. So this is 60 degrees times k. Oh, okay. And what's k? K is equal to 0, 1, 2, 3, 4, and 5. Oh, okay. Okay, so this is going to be Okay, 1. The radius is 1. So let's list out all 6, okay, solutions, complex solutions here. Okay, what are all 6 complex solutions going to look like? Okay, well, if I let k be 0, then I get just 1 CIS 45 degrees. Okay, and then the next one, 1 CIS, what's 45 plus 60? Okay, that's 105, I believe. 105 degrees. Okay, and then the next is going to be 1 CIS, add 60 to 105, and I should just keep a running tally here. 45 plus 60 is 105, plus 60 is 165. Okay, 165 degrees. Okay, and then keep another running tally. Add another 60. So we're just going to keep adding 60s 3 more times. So this is 1 CIS. Okay, add 60 again. I get 225. Okay, that's nice. 225. Okay, and then 1 CIS. Add 60 again, plus 60 is 285, plus 60, that is 345. So 285 degrees and 1 CIS. I'm going to move this down. Okay. Okay, and then 1 CIS 345 degrees. Okay. Okay, so you may not readily see this, but each of these values here, because 45 is divisible by 15 and 60 is also divisible by 15, every single one of these is divisible by 15. Okay, so it's asked me to graph them as vectors on the complex plane. Okay. So the idea here, okay, is that, okay, again, if we're in real and imaginary space, okay, okay, then our radius is always going to be 1. Okay, it's always going to be 1. The radius will always be 1. And so the radius is 1, and we just have to figure out, well, what's the angle going to be? Well, for the first one, it's going to be an angle of 45 degrees. I know where that is. That's right here. Okay, that's going to be 45 degrees here. Okay, but where is 105 located? 105 is 15 degrees from 90. If I add 90 and 15, I get 105. So what I'm going to do is I'm going to break up, because 90 is divisible by 15. If I take 90 and I divide it by 15, you're saying, well, why are you taking 90 and dividing by 15? Because that's 1 quadrant, and it's 6 of them, right? So I take a 30 degree angle and I divide it in half, I get 15. So if I were to take these, and I'm going to zoom in, okay, and this is divided in half. This is 45. Okay, what I really want is I want to get these in 15 degree increments so that I can show you, you know, what the graph, what I can do to make the graph a little bit easier to graph these. So again, this, just get rid of that stupid. Let me just draw it one more time. Okay, so again, these are at 1. This is -1. This is -1. This is +1, right? That should be maybe a little bit closer. +1. Okay, so again, this is a 90 degree angle here, right? So what I'd like to do is I'd like to split that 90° into 6 equal parts. Well, we already know how to split it into 3 equal parts. That's by doing a 30° angle, 30° angle, okay, and a 60° angle. Okay. Now, what happens if I split the 30° angle in half? I get 15° angle. What happens if I split the next portion in half? I get a 45° angle. So this is 15, 30, 45, 60. And then what happens if I, gosh, stupid eraser is just too big. Again, can't erase. Okay, and then what happens if I split this guy in half? Okay, what do I get? I get 60 plus 15, which is 75. Okay, and then I get 90. So I'm going to do that all the way around. Okay, and you'll see that I can easily graph all of these angles because they're all divisible. They're all multiples of 15 on this graph now. So if I split this guy up into a 60° reference angle and a 30° reference angle, okay, a 60° reference angle and a 30° reference angle, and a 60° reference angle and a 30° reference angle. Now I go back and I just split those up into, instead of 30° increments, 15° increments. This one's a little off. Okay. So all the dashed lines, okay, all the solid lines are your usual 30, 60, 90. Okay, and all the dashed lines are the ones that are in between that, which are at the 15s. Okay, and so dash that, and dash that. Okay, so where are these angles located? Well, this is at 105, right? Degrees, and this one's at 120, and this one is at 135 degrees, and this one is at 150, and this one's at 165, and this one is at 180. This one's at 0, and this one is at okay, 180 plus 15 is what, 195, and this is my regular 210. This is going to be 225, which is nice because that's on the 45° reference angle. And this is 240. And then this is going to be 255. And this is 270. And 270 degrees. This is 270. Okay, and then this is going to be add 15 to that, that's 285. Add 15 to that, that's my regular 300. This is 315. This is 330. And this is 345. Okay, so now let's go back and look at our values that we have here for our angles. We have 45. Okay, so I'm going to put this in a different color. Maybe I'll do green. Okay. So at 45 degrees going out 1 unit, there's my vector. Okay, going out 105 degrees green, there's my vector. 45, 105, 165 is next. Going out 1 unit. Okay, there's my vector. And then 225. Okay, and then 285. And then 345 is the last one here. Okay. So we ended up on the real and imaginary axis ended up showing these vectors, okay, at these angles, okay. Now you could go back and figure out what these are in rectangular components, right? Where these are located, like the 45, that's just going to be radical 2 over 2, radical 2 over 2, because it's 1, right? These are all on the unit circle. Why are they all in the unit circle? Okay, because they all have a radius of 1, okay? So they're all on the unit circle. So all these points are on the unit circle. So you just have to find out, well, what's the cosine and sine of 45 degrees? Boom, right there. So this would be, you could go back and say, well, this is radical 2 over 2 plus radical 2 over 2i. That's where it's located in rectangular imaginary components, right? And you could do the same thing for 105, 165, 225, 285, and so on. Okay, well, this one was a lot, but we tackled it, and I will see you in the next video.